Welcome, everybody. Today we have a guest speaker, Fabian Ruffy, currently I believe you're interning at Intel right now, and you are a doctoral student at some university, I've forgotten which.
NYU, correct.
Okay, excellent. And your focus area is like probably what, formal language things, computer science stuff?
Yeah, largely data plane testing.
Please describe
currently.
your specialty however you wish.
Yes.
And
so mostly developing tools for P4 and largely testing of P4 targets. And so that's also what this talk is going to be about today. And this is a tool we have developed over the last 2 years called P4Testgen. And this is a collaboration between Intel and NYU and collaborators from Liftsoft in Ukraine. Now, before I get into it, I would like to have a quick refresher on P4 targets and the P4 target ecosystem, how it really works, because P4Testgen is a tool that is designed to be very target independent. And so it helps to, even though people here understand P4, to get a little bit of a refresher on what it means to develop for P4 targets. And then I'm going to talk about how to test these targets, and then why we believe Testgen is necessary. In general, this talk will be more high level and more a teaser of this tool instead of having technical details. Now, as you know, P416 as a language is designed to compile to many targets. So if you have your P4 program, you typically need a architecture specification or architecture file. And that could be for your operating system stack, for example, when you have an eBPF P4 program, for your switch, the Tofino or the V1 model, or various kinds of other targets that are being developed, for example, PSA or PNA. Now you have this target and you want to build and run your switch. What do you usually do when you have this independent software workflow? Well, you write your P4 program, you compile it with your P4 architecture model, and then you get this target-specific configuration binary. You load this binary into your target, and that forms your target's data plane. Now, once you have this, you will also probably have some form of control plane that administers your target. And using this control plane that's user supplied, you can develop a runtime that helps you configure your target live during running, and you can also just configure it in general.
Good question, Fabian. If folks have questions during it, do you want me to interrupt?
Oh, yeah.
Okay.
Feel free to interrupt. I'm not going to look at the chat. I don't have it here, but
I'll look at the chat. If anybody has a question that they want to interject, feel free to put it in chat or raise your hand, and I'll keep an eye on that.
Great, thanks. Okay, so now you have this target workflow, but you want to make sure it works correctly. So we get to the next step, which is once you have this, you want to test your target. And typically in the P4 world, how this is currently done is the following workflow. So you typically write a test, that is a test file, for a particular P4 program. And you have these two parts. Now you compile your P4 program, and you run your test file through a test parser. And with that, you form this test environment. So once you have compiled your P4 program, you load it into the target using the typical workflow. And using the test parser, you synthesize a set of input packets and a specific configuration for your target. And using this input packet and this control plane configuration, you would expect a specific kind of output with your target. Now, using your test runner, you run this through your target and you get an output. And once you compare these two, you will see whether you have an issue or not in your test environment. Now, this sounds nice in theory, but let's think about how this is currently done in practice. Now, what you see here is such a test. This is a test file, and this is a PTF test that is written for a switch. Now, what this test really does, it does nothing more than just running a TCP packet through a switch and just checking whether this packet goes through the entire pipeline. However, what you see here is a lot of constants that need to be set and a lot of arbitrary hex code that has to be configured in some way. Now, imagine trying to run or write these tests for hundreds and hundreds of different scenarios. This can get quite tedious after a while. And currently, we have only this way of producing tests. Now, this gets me to our main point, which is also the bigger motivation for this entire tool, is that you have these many written tests, but there are two problems with them. A, the return of these investments is the return of investment for these particular tests is quite unclear, because when you write these, you don't really know what they actually covered, and you also don't know if you write a dozen or 24 or 60 tests, have you covered enough of this particular target or this P4 program? How do you know that? Now, coupled with that, writing these packet tests is quite hard, since you just write hex code or sequences of bits, and you have to match these bits precisely with your control plane configuration. At the same time, if you have a complex switch, which has many tables, you have to configure all of these tables to just get a packet through. And so you have to write a lot of tedious boilerplate just to get a single feature tested. Now, the consequence of this is largely that we don't really write that many end-to-end tests for our switch programs. So practically speaking, engineers write a couple, at most a dozen, but most of the time just one or two of these tests for the particular programs they want to test. And the consequence, of course, is the testing is quite ill-defined. Now, based on this status currently, we believe we can do much better. And the reason why we believe this is that P4 is a very well constrained and well-specified language. And it gives you essentially a machine-readable contract on how the network device will behave. Now, P4 is open source and it's well-specified, and we have full access to its semantics. And we also know how our device that we want to test will interpret this P4 code, because we have a certain model of the device in our mind. Well, in research, there's a rich body of software engineering and formal methods testing for general purpose programs. And having that, we believe we can actually leverage this to automate testing as much as possible in the P4 world. Now, what is our main idea? Is we want to generate tests using symbolic execution. And what this means is that we take a P4 program, we walk a random path through that program, so the program nodes are items in the program, and we collect these symbolic path constraints. These path constraints, essentially, they specify what inputs are necessary to traverse a particular path. And we can encode this as a first-order logic formula. Then we use an SMT solver or SAT solver that gives us the model to traverse this path. And then we convert this model into an input and output test that we can execute. A nice bonus is that once we emit this test, we can also associate a program trace with it. And so we know exactly what kind of feature we're covering with this particular test. So this idea is not new. So Andy Finger here, for example, he was involved with a tool called P4Testgen, which has done this for the V1 model program. And it already generated input-output tests for this particular model. However, while these ideas exist, and they have been existing for a long time, we are faced with a special problem. And that comes back to this target independence of P4. Because we have so many targets, limiting yourself to a particular input target might be very, very short-sighted. Because we have our ecosystem develops, and if you specialize towards a particular device, you will have to produce another test gen developing tool constantly. And so we do not want to tailor ourselves to a particular device. At the same time, we want to be accurate and as precise as possible. And so we have to model these whole program semantics. So we need to understand how our target actually interprets the P4 code. So we cannot be just generic and just write tests for the P4 specification, because the P4 specification leaves a lot of holes and room for interpretation. And so far, there has been no tool that really bridges this gap and allows us to be as flexible as possible, while also being very precise. Any concerns or questions at this point? Because now I will start talking about our tool P4Testgen. Nope. Okay.
Yep.
Moving on. Okay, great. So now we have these requirements, and based on that, we develop P4Testgen. And so what P4Testgen does, as explained, it will generate inputs and outputs. And so with that, we can not only check for crashes, but we can also check for semantically incorrect behavior, meaning we have issues in the compiler or in our control plane that will lead to incorrect packet output if you have a certain input. P4Testgen is target independent. And so it is designed to support test case generation for any particular P4 target. So NICs, switches, the operating system stack, the IPU, DPUs, anything that supports P4. And we explicitly made it such that anyone can add their own target as an extension. And that also allows for code reuse. P4Testgen also implements these whole program semantics. And so this tool covers the entire semantics of the P4 program and also the semantics of the device that really executes the program. And with that, we get a device specification for single packet tests, meaning we describe how a single packet is executed on our device. So what is P4Testgen's general workflow? So ideally, you would take a P4 program, and then you run it through our front end. We apply target-specific program optimizations for different kinds of backends that make the P4 code and the P4IR amenable for symbolic execution. Then we feed it into our Oracle, and here we step through the program and do analysis of the particular test, and we collect path constraints. Once we have collected these constraints, we feed them in our SMT solver. In this case, we work with D3. And then we generate a suite of tests. We have an abstract suite of tests we collect, and then we can realize and serialize these particular abstract tests into various kinds of test frameworks that are in use. So in the P4 world, in the open source world, what is commonly used right now is the SDF and the PTF frameworks. There's also the possibility to use protobuf tests or all kinds of specific test frameworks that are used. For example, we are currently working on something that also just generates PCAP files for you. Once you have this, we will produce a series of emitted test cases, and you can use these test cases for anything you want. Now, there's something I really want to clarify, and that's important. So P4Testgen is designed to check the target stack, meaning anything that is responsible for executing your P4 program. But we do not check the semantic correctness or issues with the P4 code itself. So we are testing what the target is. We're not testing that, for example, you're accessing an invalid header or you have a logic issue in your P4 program. P4Testgen does not do enforcement on that, and it actually interprets it to the best of its abilities what the P4 specification says on these behaviors. To make this a little bit clearer, I will now show a little demo how we execute and generate tests for a simple switch program. If you have any questions at this point, please let me know. Okay,
yeah, I have a question.
Okay, yes.
So it seems like this is really good at testing what the P4 code actually does, but
Yes.
How can we verify that it's testing what it's supposed to do, right? What if it's functioning as intended as opposed to as is?
So there are other tools that have been developed for that particular purpose. For example, there is P4V, and as far as I know, a variety of academic research that allows you to instrument assertions in the P4 code. And when you run it, these tools will produce inputs, outputs, or examples that might violate these assertions. Because these tools already exist, and so we were not focused on developing this particular kind of program testing.
Yeah, I think it's fair to say that this tool isn't intended to be the only functional testing tool you'll ever need for P4 programs.
Yes.
I see. The other thing, it seems like it would be useful for regression testing, basically repeating those test suites over after you change the P4 code.
Yes, that is one of the use cases that we've been working with. Ideally, you would like to generate a huge test suite for your particular P4 program, and then you use this once you make changes to see if there are any changes, or which kind of test might fail if you do make your changes.
Yep, thank you.
Okay, let me walk through the.
I guess I would make a comment, Fabian, that
Yeah.
I know you. This is a fantastic tool for quickly creating tests, but yeah, there are people that only create very small tests. But for production P4 programs, I've seen people do often spend the time and effort required to make more extensive test suites, and they use, higher level functions in Python to create packets than raw byte strings and things like that. But yeah, not a criticism, just a comment that when it's important, people do spend that time.
Yes. So I'm thinking you're talking about PTF and the library of PTF.
Yeah. Like Tofino switch.p4, for example, does have quite there's probably been more time spent writing tests for it than there has been writing the code, I bet.
Yes. So in general, it still has holes based on our experience.
Oh yeah. They don't strive for complete test coverage, but they do catch a lot of bugs with it.
Yes, that is true. And in general, it makes it more user-friendly if you can use these functions. The nice part is Testgen could use these general purpose functions if needed. As far as I know, these are written for particular header stacks, so TCP testing or IP testing, as far as I know, or Q&Q.
Yeah.
But correct me if I'm wrong.
No, those tests are very difficult to achieve broad coverage. I agree.
Yes. Yeah. And exactly one use case of Testgen we've been working on, and that we've been asked by various switch teams, is that you can ask the tool a query to generate only tests for a particular feature. So if there's a new switch feature being developed in a particular protocol stack you want to test, you might only want to generate this particular suite of tests and run it.
Yeah, that's a very
excuse me,
useful feature.
are the test cases human readable? Or are they like binary patterns?
So the test cases, it depends. They're supposed to be human readable because they're written by developers. And what Testgen itself does, it just has an abstract test spec, and it generates these testing files that are used by normal developers. So for example, here in this example, I will step through it. This is an SDF file, which is used by compiler developers to test the compiler itself. It is the most simple format, but it is human readable.
Okay, I meant your tool. It showed it generating test cases, files of test cases.
Yes.
Maybe at the end of the demo, you might show the output of them.
Yep.
Yeah,
that'd be great. All right, thank you.
Okay, I think the demo might just clear up things. So this is a P4 program, and it's a very simple program. In essence, what it does is it parses an Ethernet header. Once it has parsed that header, it will apply a table, and this table just matches on the destination address and an exact match. And if it matches and the action rewrite source is part of the merge action entry, it will set the address to just all Fs. So most basic simple program. Now we can apply Testgen to it. Now the command looks a little complicated, but that's because we're using full pass. But you just use our tool, you run it on this, and it will spit out a series of tests. The tests, this is just debugging output, but the tests that have been generated, you can see now here in this series of tests, and we generate 4 tests. Why do we generate 4 tests? Because there's only 4 unique input-output pairs that traverse a different path. And the tests we generate, those are, as I mentioned before, those are called SDF tests. It's a specific framework for testing that allows you to insert simple commands and have simple expectations on this particular test. Now, what happens here is that in the first test we write, we have a certain condition, which is that what we test here is that we have this extract call, and we expect that the extract will fail. So the packet is too short. And once the packet is too short, we skip into the verify control and move to ingress. Since the header is invalid, we don't execute this table. And so the packet itself will just be emitted as is and nothing happens. That is the first path we can traverse with our tool. Now, for the second test, that's a more interesting one, is we actually have a packet that is now long enough. You can see here that in our trace, we see that we have these values extracted and associated with the header, Ethernet header. And now we execute our table and we use and apply the rewrite source function. So now what we do in Testgen is we, using our test framework, we insert a control plane entry saying, okay, we want to match on this value in the destination address. And if we match on this value, we expect that the packet we emit and that we will be our output, it will have its source address rewritten to this particular series of values. That is one test case. Now, the other two test cases we generate are variations of this. So we could also just execute no action, meaning we do nothing, and then we expect that nothing happens. And the last test is not inserting a table entry at all, having a valid packet, and expecting that the default action of this particular table is executed. And so since nothing happens, also the packet remains with all zeros. And in a gist, this is what Testgen is currently doing. Given a P4 program, it tries to traverse all the paths in that particular program and tries to achieve maximum coverage of all statements in that particular P4 program, including the externs. Now, if you run this test suite, you can also find issues with your targets. And we have done this in various ways. So any questions on this particular setup or demonstration?
I suspect you can also output PTF tests, or maybe you already said that.
Yes, for the purpose of this, I have not used PTF tests because they have a lot more boilerplate.
Yep.
Basically, we have this test backend you see here. Currently, it is STF, but we can also associate it with PTF. Oh, I think I made a typo here. Yeah, it's PTF before. But once you do this,
yep,
what you
nice.
should see is a PTF test, and that includes everything. It's just a
Different syntax.
Yeah.
Cool.
Yep. So actually that's one of the most important features, because there's in the P4 ecosystem there's a lot of different users using different frameworks. So we made this an important. It was important for us that we are able to generate different kinds of test formats. Okay. Let's step back. Oh, okay. So based on this, having seen this, what you can generate with that, we think that there are certain use cases for this tool, and we know there are certain use cases for this tool. Especially compiler developers that are developing a new backend for P4, a target backend, they can use this to validate that their backend optimization passes and their translation is working as intended. Since Testgen is target independent, it also has just a general view of the model you develop. You don't use the same optimization passes that you would use for your target backend. And with that, we can also use differential testing to identify issues. And we have been doing this for the open source compiler backends for the V1 model and the Tofino and Tofino 1 and Tofino 2 compiler. Similarly, what we've been also working on is that for network operators, as said, for regression testing, you can generate a suite of tests for your programmable device and your deployed programs and just run these tests continuously to identify issues. Because otherwise you would have to manually write this, and there would be a lot of human hours that would go into writing these tests. The hope is that once P4Testgen is mature enough, that you can just test a particular feature and just have a suite for this particular feature. Similarly, because P4Testgen essentially gives you this soft specification for your device for a particular test, we believe that equipment vendors or resellers, they can certify that they are compliant with both the P4 specification, since we adhere to this, and also the manufacturer specification for a target device. And lastly, a collaboration that we are currently working on is that if you would like to model fixed function devices, so existing switchers that are not programmable, you could do this in P4. And once you have this P4 specification, you can generate tests using Testgen to validate your actually fixed function device. And once you have this, you can identify issues with your software stack that programs this particular fixed function device.
Or I guess potentially you could identify ways in which your P4 program does not model that fixed function device.
Yes, you can also find issues with the fact that your P4 model of the fixed function device is incorrect, or that there's an issue with something in the fixed function device, the behavior is off from what you would expect based on your model that you have developed.
Yep.
And yeah, this has happened in practice. So there's a paper in SIGCOMM by Google actually called SwitchV. And so they're doing something very similar to this. Now, let's get a little technical. Let me see how much time I have. With an hour, that's fine. Let me explain a little bit on how we actually achieve all of this. So we have to develop this whole program semantics that allows us to both be very generic, but also be very precise for a particular specification or target. And what we want is we have 3 requirements. First, P4Testgen must be an oracle for the P4 language, meaning you as a P4 extension developer or consumer of P4Testgen, you never should worry about P4 semantics. We can take care of this. Second, we must be as broad as the P4 language specification. So wherever the P4 spec leaves room, we should also be able to accommodate this room. So various targets have various interpretations when a packet is being dropped. And so we should be able to model this. Third, this is also quite important. Each target, of course, because of hardware or developer constraints, has its own quirks. And this can lead to various kinds of non-determinism or specific environments constraints. So there could be externs that produce random values, or if you initialize an uninitialized value, the initial value could be random. Now, in a target environment constraints, some packets might just be dropped because they're too short or too long. And there might also be targets that do not adhere to the P4 specification quite as religiously as they should or as they can. And this can also lead to friction. Now, this leads to a series of challenges. And the first challenge is, how do you really model a target's data and control flow? So anyone that has been developing tools or semantic tools for the P4 language might run into this issue, which is that you have these programmable blocks, so your parser, your control, your deparser, anything, but it's not quite clear what's happening between these particular blocks. This is something that is completely up in the air, and you have to develop semantics for this. Now, how we approach this problem is twofold. First, we have this abstract machine we have developed, which you take a P4 program and you convert it into a tree of P4 program nodes. We actually use the P4C IR, which is the P4 compiler IR. We then walk each branch and we build our program state. And then at each leaf node of this particular branching or tree, we emit a test and then backtrack. So we have a depth-first traversal of the entire program. The important features are that state is fully independent. So whenever you are in a particular program branch, you can easily switch. And that while we're walking through this, every node can alter or change program execution. And it can also be subclassed or overwritten by a target extension. So each target extension, it can implement its own completely own control flow. And also each target can also change the semantics of every program node. For example, you would step into a table or you would traverse a table execution. Different targets have different notion of what it means to execute a table. And so you can implement an extension for this. So we have a specific technique we use, which is continuation passing style, but I will not get into the details of this. Now, the second item we use are these so-called pipeline templates. And similar to a P4 program having an architecture file, each target here must describe an architecture model. And what this means is what it describes the particular control flow that can happen in between the programmable blocks and how metadata, for example, is interpreted and can affect program execution. So programs can be dropped, they can be recirculated or modified if you have a packet going through. Now, our current architecture model is a specific C++ DSL we use, and then we convert this into our custom control flow. However, we would like to express this in P4 only, and this is something we're working on. A useful side effect of this is that once you have written your control flow for a particular extension or target, you're likely to be able to reuse a lot of this for another target or extension. We've been doing this for Tofino 1 and 2. So we've written our control flow entirely for Tofino 1. However, because it's very similar to Tofino 2, we were able to just reuse a lot of this code, making it simple for us to implement a new extension. Now, the second big challenge is, of course, dealing with all of this non-determinism and target complexity. And now, where this is coming from is that some program state is just simply undefined or random, and we have no control over what's happening there. So if a table reads an initialized key field, it's unclear whether we match or not. And also you might have a random X and it just remains random values. And if you branch on this, what kind of branch do you execute? Secondly, not all target functions or extents, they cannot be really modeled using first order logic. So C3 formula. So a hash function is really difficult to express in that notion or in that terms. And solving them can also be quite slow. However, we still execute this function, right? So we need a concrete mapping to understand what this function will produce. Now, our two solutions to this are taint tracking. So taint tracking can handle non-determinism. And what we really do is just we mark state affected by unreliable program segments as tainted. And once we read or write to this taint, we resolve it as needed. So if you have an if statement and the condition is tainted, you could execute either branch, meaning that all the assignments we do in these particular branches in the statement block, they will produce new taint, and taint will propagate. On the other hand, if you multiply a tainted variable by 0, that taint will disappear because the result is always 0. Now, taint will become very important when generating a test. And it becomes important for setting don't care variables for unreliable outputs. So if your test framework allows this, you can set certain segments of the packet as unreliable. And so it can still produce a test that deterministically passes, because we know that a particular segment is not important. And if we know that a particular test we cannot handle, so if the output port is always random and we cannot capture this random output port, we can discard the test or emit a warning about this particular flaky test.
Quick question on
Yeah.
variation of that. Like, what if you had this would be very unusual, I imagine, but well, actually maybe this would be quite common, a random choice that dropped a packet or sent the packet out with a modified header.
A random choice that drops the packet or sends it out with a modified header. Yes, that is a case that is, because we don't have a test framework that can express this, we have to basically use the second option in option 3. So discarding the test or marking it as unreliable, because we cannot fix the randomness. And we also have no means in the test framework to say, okay, this particular test will have these two possibilities of output. Testgen is essentially limited by how your test framework is able to mitigate these kinds of scenarios. If that makes sense.
I suppose a developer, like you could give advice to developers saying,
yeah,
if you provide me a way that some header field can be replaced the random output, yes, then you can control it from an input bucket kind of techniques, yes, could help test.
Yeah, so essentially taint tracking is just a technique we use to keep track of this. But at the end, we just have essentially sections we know are unreliable, but how we deal with them or how we interpret them is up to us. And it depends on the infrastructure we have. So I don't know what kind of, how you would write for your scenario, what a test would look like in a normal scenario.
Yeah, I guess in the kind of like the kind of thing I was thinking of, like sometimes people write tests like verify that 50% of the packets are dropped and 50% of the packets come out as expected, but those are
if that is possible to do, we can also generate this.
Okay.
But I'm actually curious because we hit this problem quite commonly, but I haven't seen any way to formulate this in PTF, for example.
I mean, like I say, a more predictable way would be if you said, if you're willing to modify your P program a little bit for testing purposes, instead of doing a random generator, use this IP identification field for the random value instead. And
yes,
you can control it from the input. Yeah.
It makes it easier for us.
Yeah.
Actually, we have executing this on larger programs, we have spotted a lot of non-determinism because we've ran into these scenarios a lot, and there were causes where things were just not predictable. That was part of what happened to us.
Yeah, I believe it.
So when you, excuse me, when you discard a test, do you output diagnostics to help us, identify the problem, or?
Not right now. We have a small diagnostic saying, okay, for this particular test, for example, the output port will be reliable, and that's why we cannot produce a test for this.
Okay, at least you let us know that it was dropped.
Yes. This is still early stages, so we have not made this a particular feature, but it is easily doable to just collect these unreliable tests and associate a diagnostic with it, why they're deemed unreliable. So
great. Yeah, thank you.
Now the second part is more a fancy detail in the sense of now you have complicated externals, really complicated externals such as hashing or cryptographic externals, which are not, we cannot mark them, we cannot use just generic symbolic execution. However, we could mark them as tainted. So anything they produce is taint, meaning it's not, we don't know what the output will be. So we just assume wildcards. However, that might lead to a lot of useless tests because as we just discussed, there is a solution, but we cannot predict it. And we would like to produce a test for it. Now, here we use a fancy solution called concolic execution, which essentially is just a fallback where we pick a set of random inputs for the function that are possible given the current constraints, and then we just execute the actual function, and then we get an output from that function. Now we have a series of inputs and we have a series of outputs, and we encode these as new constraints for the SMT solver, try to find a model, and if that's the case, we can emit a test. If not, we have to either try again or we need to abandon this particular branch because we cannot find a model that satisfies the execution. Okay, those are all the technical details. And now I can briefly talk about the current status of the tool and where we are. We've contributed this tool in August to the official P4 compiler, and it's now running as part of the CI there. And we are also actively developing it in open source. We have developed, let's say, 3.5 extensions so far. One is the current well-known V1 model that runs on BMV2. And what we do here is we also support this new P4 constraints framework that really specifies what kind of table entries are eligible to be used. We also extensively support TNA and T2NA. And well, there's a certain amount of quirks about these tools, which are modeled in our extension. These extensions are still proprietary and not public, but we are working with Intel together on figuring out how to make this widely or easily available. The third one is just a proof of concept, which is the ABPF model, which is a completely different model compared to the other switches. There's the Linux kernel eBPF, which also can be programmed using just P4, but it has certain restrictions. For example, it cannot modify packets and it has no deparser. So we had to model this too. And it was trivial to do once we had the other extensions. We're looking into more extensions we could develop, and we're happy to hear suggestions or feedback on what else we could generate tests for. So in terms of evaluation, checking that this tool actually works, is what we do is we run this on hundreds and hundreds of P4 programs. And per commit we do in our CI is we run this on 2,000 program tests for all different test backends. And just by doing this, we have, for now, 25 bugs, well, 9 of them in BMV2 and 16 in the Tofino switch stack, where we found issues and discrepancies in what we would expect and what the output is. And, well, at this point, unsurprisingly, most of them are compiler bugs, since they are incorrect transformations in a backend that led to a semantically incorrect output. One lesson we had is that because we are so detailed, for the larger P4 programs, such as the switch.p4 program by Tofino, we generate too many tests and we overwhelm developers. So we generate millions of these. And there's a high signal to noise ratio, and we're trying to work on mitigations that can help with reducing this noise. So that also brings me to future work. To make this more usable, this tool is we are thinking about developing path queries in which you can only produce targeted tests. So an example query would be here, I want to produce tests that hit this particular table with a particular header that is only this particular header what it should be valid. And then you just generate these particular tests. The other strategy we are trying to explore is new ways to traverse the tree of the program. Meaning we could have strategies that maximize coverage very quickly, and coverage meaning statement coverage, for example. And here we prioritize statements that have not been covered so far, meaning we at least cover all the statements in the P4 program quickly. Lastly, we also want to implement more extensions, and we want to see how far our expressiveness goes and how general we truly are. We are currently eyeing the P4 target and the PSA architecture, but this is also work in progress. Now, let me conclude. So what I presented today was a teaser of P4Testgen, which is this new test case oracle for P4 that produces input and output packets. What we do is we develop and run whole program semantics that model a P4 target pipeline and allows us to execute very detailed tests for a particular P4 program. What we have is a certain set of execution and extensions for V1 model, DNA, T2NA, and the eBPF model. And we're already finding bugs. And the reason we haven't done more is we have not filed them yet. We have a collection of tests we need to analyze, and we believe we can easily increase our bug count quickly. With that, I conclude. If there are any questions, feel free to ask.
Yeah, it looks really good, Ruffy. Thanks a lot.
Yeah. Thanks.
Any other questions? I will point out one way in which I wouldn't necessarily normally think of using this kind of tool, and it doesn't come up very often, but I did this with my version of the tool, but I had like two different ways in P4 of calculating the same result, one which I was sure was right, but wasn't very efficient in its result, and the other one was an optimized, thing that I was expecting to, and then I wanted to, so you can, if you write a P4 program that has, the optimized one that you're not sure about and the safe, simple one that isn't very optimized, you can calculate both and then have an assert or a different output if they ever differ, and then have the tool try to find a case where it can make them different.
Oh, so you compared both of the programs using the same inputs? or
Well, a single program that uses two different ways of calculating some intermediate result,
oh, I see. Okay. Ah,
and
that's
then
interesting.
have an output bit of the header that's different if that's like 1 if they differ, and 0 if they're the same, and then try to make that bit 1.
Oh, that's definitely. I mean, yes, our tool will just generate a test that tries to hit that.
Yep.
That's interesting. Yeah, that's an interesting.
It can
Use
create
case.
for some. It can make for some very long Z3 solver times, depending on what you're comparing.
Yeah. Not bad. Yeah, that's something we could do. So if you have that's a neat way of differential testing.
Yeah.
Yeah,
No,
it's
just
essentially
it's just a
exploit.
it's not for production code. It's more for like, oh, you want to do a spot check on this one little bit of code, and you write a program that.
Yeah. But
compares
that's very useful for compiler developers.
Yeah, could be. In my case, it was functional testing of my P4 code that I wanted to was my focus for
Yeah.
that little section.
So, for example, if you have an optimization for something,
Yeah.
and
Yep.
you want to see if the optimization adheres to some value you want to achieve, you could use this technique. Yeah.
Thanks, Fabian. I'm
Yep.
going to stop the
Gladly.
recording now.